All right, here we go into our next section. This is the beginning of exponential and logarithmic functions in calculus. In this section, we're going to take derivatives and look at the slopes of these functions. And so a lot of the curve sketching stuff that we've done in the previous sections, we're going to have some applications that we look at that we use this for, but we're also going to look at a technique that involves logarithmic differentiation, it's called, which ends up being kind of a different beast. But other than that, no real surprises with what's going on in this section. We do need to start off with the fact that let's just do a little bit of review of what we know about log functions and exponential functions from last semester, from Math 30-1. What did we know about this? And let's start off with some simple exponential functions. We have a number one, y is equal to a to the x. If a is greater than 1, that was exponential growth, and our graph looked something like this. So that's not quite right. Our graph looks something like this. Let's try this again. Okay. What did we know about this graph? We know that we have a horizontal asymptote with this. We know that we have a y-intercept that happens at the point 0, 1, because when x is 0, anything to the 0 is 1, and so that's what this looks like. If we had a coefficient in front of ax squared, that would have been a vertical stretch, and it would have affected that. But in general, the shape is going to look like this. The domain of this is all real numbers. The range of this is only positive numbers. We have a horizontal asymptote at y equals 0, and a vertical asymptote not at all. Okay, so this was exponential growth. We looked at bacteria growth and population growth. We looked at money and compound interest, and all of these kind of were described by an exponential growth curve. If we have the same thing, y is equal to a to the x, but instead our base of a is between 0 and 1, this is no longer exponential growth. This is now exponential decay, and it still has a lot of the same characteristics. We still have a horizontal asymptote on this graph. We still have 0, 1 is going to be your y-intercept, but we end up with a lot of the same characteristics. The domain is all real numbers. The range is everything greater than 0. Your horizontal asymptote is y equals 0, and your vertical asymptote is none. When we did this last semester in 30-1, we looked at taking the inverse of an exponential function. We took an inverse by swapping your x and your y in the equation. You let your y equal x, you let your x equal y, and then how do we solve it for y? We had to invent this new notation called logarithms, and that's really all that a logarithm is. Y is equal to log x base a means the same thing. Remember that a to the y is equal to x. So we took this equation, swap around your x and y, it becomes this. This is the equivalent to this form. And so because your x becomes your y and your y becomes your x, now we have a vertical asymptote. Now instead of going through 0, 1, this goes through 1, 0. You have a domain that is x has got to be greater than 0, not even equal to, that's an asymptote there, so x has to be greater than 0. Our range is all real numbers. Horizontal asymptote, no, and our vertical asymptote is x equals 0. All of this can be described by the fact that your x becomes your y and your y becomes your x. Those two variables swap places when you take your inverse, and this is how it's expressed. This is what it looks like when a is greater than 1, when you have the base of the logarithm is a number greater than 1. Of course, if you had a base that was between 0 and 1, then it would be kind of a similar shape, but it would be, of course, vertical asymptote, and it would be decreasing like this. Now, keep in mind that this is not an asymptote here. We don't have a horizontal asymptote, nor do we have an oblique asymptote that will keep increasing forever, but just at a lower and lower rate. All right. This next bit talks a little bit about, okay, so we have some special symbols that we use in math. And so some of these numbers that we've been seeing for years, like pi and square root 2. Some numbers we haven't seen yet, e, and this other one, that I, we're probably not going to deal with I too much in this course. I is the unit of complex numbers. So the square root of -1 gets a little bit weird, but that is the case. Some of you will maybe see that in university, depending on where you're going. In the next couple of years anyway. I think engineering students will see it in year 1 or year 2, probably in year 1. If you're a math student, you actually probably don't see it until second year, but regardless, this other number in this list that's new to us, that is E, is certainly a huge thing in this course. We use the letter E because it's named after a Swiss mathematician named Leonhard Euler. It's pronounced Euler, not Euler. And it represents a few different things. And you've probably come across it. You've maybe seen some math YouTube videos that discuss what's going on with E. It ends up being a remarkably important number in calculus. What it ends up being is it's a irrational number. It's 2.718. If we look at some more digits of it, it's 2.71828. It does have, if we want to keep going with digits, 1828, 1828. It actually starts to look like a repeating pattern. 2.71828, 1828, but it's not. It is not a repeating pattern. It does go into chaotic patterns and non-patterns after that, and so it is not rational. What it ends up being, there's a few different ways of defining it. It looks like this. The limit as x goes to 0 of 1 plus x to the 1 over x. And when x gets really close to 0, there's a few things that happen with this. When x gets very close to 0, then this gets close to 0, and we have a number that's very close to 1 raised to this exponent 1 over x. So that raised to an exponent that becomes very large. And so we have this number that's very, very close to 1 being raised to this very, very large exponent. And what does this become? As x gets to be very large, this starts to settle in. It comes closer to this special number called Euler's number, 2.71828. We will just refer to it as E. We won't use the decimal expansion of it, hardly ever, but we will use this quite a lot in this course. It starts off with saying, okay, so recall that the logarithm of y base a is equal to x is the same statement as saying that y is equal to a to the x. What we will use this letter E, or this number E for, quite commonly, is we will use this as the base of our exponential function. And so we will talk about x is equal to logarithm of y base e, means the same thing as y is equal to e to the x. So just think of this, you can think of this as a number of 2.718 to the x. And so it's just a constant, is what it is. But it's so special constant, it gets its own notation here. Y is equal to ln y. It stands for the natural log of y. And sometimes we will pronounce it ln. Some people pronounce it ln, some people pronounce it ln, but is natural logarithm. And it just ends up being the most special logarithm. So remember that common base for your logarithm if you had no number written there. If you have y is equal to log x, if there's no number written there, it ended up being base 10. But often in 30-1, we wrote a number there. Now in this, we will have y is equal to ln x. Sometimes it's written with a script L, but it's just a number. It's just going to be a logarithm that has a base of 2.718. So y is equal to e to the x. What does the graph of it look like? Well, it just looks like exponential growth. It looks like exponential growth. It's going to be a little steeper, a little more severe a curve than y equals 2 to the x, but probably not as steep and severe as y equals 3 to the x because it's 2.71828. It has a horizontal asymptote just where we would expect. If we have y is equal to ln x as a graph, well, that's just going to be a logarithmic graph that's going to go through 0, 1. It's going to be a sharper a curve than if we had base 2, but not as sharp a curve as if we have base 3, because that's where it sits. All right, all of that said, let's start this off by looking at some limits. So it's been a while since we've looked at limits this way, but this will kind of be a useful thing to do once we start getting into exponentials. This starts off by saying, okay, y is equal to a to the x when a is greater than 1. So this means we have exponential growth when x gets large, a to the x gets large. And in fact, when x goes to infinity, we have a getting to the exponent of a larger and larger number. And so our limit is infinity. Keep in mind that, like what we were saying earlier in this course, technically we say this limit does not exist, but also let's call it positive infinity. This will get our head around what's going on when we try to draw these things. Limit of a to the x as x goes to negative infinity. That's looking like, so we have this growth function, but we are considering what happens when we take x values that are further and further to the left. And so looking at it that way, this ends up being equal to 0. We could consider this being really the same thing as the limit as x goes to, this is really the limit as x goes to infinity of a to the negative x, which is limit as x goes to infinity, 1 over a to the x. And if we think of it that way, then the denominator is getting infinitely large, and you have this 1 over this huge number, and so that is why this goes to 0. The limit of a to x as x goes to 0, well, as x goes to 0, this is equal to a to the 0, which is equal to 1. Keep in mind that for all these questions, a is greater than 1. Therefore, the limit of a to the x plus 1 when x goes to infinity, we don't write this as infinity plus 1. That doesn't make sense. Infinity is not a numerical idea. We can't do operations and we can't do arithmetic with infinity. And so because of that, it's just still infinite, whether we add 1 to it or we subtract 1 to it. The limit of a to the x plus 1 as x goes to negative infinity is just what you would expect. This is 0 plus 1. So, of course, it's just 1. The limit of a to the x plus 1, let's not call it a times infinity, even though you might be tempted to do so. This is just infinite. The limit of a to the x plus 1 when x goes to 0 is equal to a to the 0 plus 1. We can actually evaluate that limit. That's not a big deal. And this is just a. Similarly, the limit of 2 to the x plus 1 when x goes to 0. It's just 2 to the 0 plus 1. No big deal. It can look a little clunkier like this, the limit of 7 pi quarters, it's just a constant to the 7x plus 1 as x goes to 0 is just equal to 7 pi over 4. The limit as x goes to negative infinity of 2 to the negative 3x. Okay, so now we need to be careful in here. X is going to negative infinity. We're getting increasingly large negative numbers for x, and then when we multiply by negative 3, then this is essentially the same as the limit as x goes to positive infinity of 2 to the positive 3x. And so if it helps to look at it that way, then this is positive infinity. Number 11. The limit of e to the x when x goes to 0 from above. When x goes to 0 from the right, that means we're dealing with numbers like 0.01, and this will just be equal to 1. The limit of ln x as x goes to infinity. So ln x is just a logarithmic that just happens to have a base of e, and when x goes to infinity, this is going to infinity. Nothing really new here, just a little bit of warm up and a little bit of reminding ourselves what's going on with limit and just the style of thinking that you have to employ here. The limit as x goes to infinity of ln of x minus 4. So we have, as x goes to positive infinity, this is the natural log of infinity minus 4, whatever that means. And so this ends up being infinite. The limit of natural log of x minus 4 as x goes to 4 from above. Okay, so this ends up being, we have to stop and pause for a second here and think about what's going on with this. So we have as x goes to 4 from above, this is the natural log of x minus 4. So this is the natural log curve that's been shifted to the right by 4. So we have our vertical asymptote is x minus 4. And so as x goes to 4 from above, this is looking at as x gets really close to 4, and so this ends up being kind of down here, so to speak. And so this ends up equaling negative infinity. So conceptually, there's a little bit more to that. And then number 15. So we've seen some stuff like this, the limit of x over, 4 to the x over 2 minus x. So we've seen the case, we know what to do when, if that exponent was just your function, if we had the limit as x goes to infinity of x over 2 minus x, we knew what to do with something like this. We divided top and bottom by x, or we multiplied top and bottom by 1 over x. So that really ends up being our strategy here. So this ends up being equal to the limit as x goes to infinity of 4 x. And we're going to multiply top and bottom. And this ends up being equal to the limit as x goes to infinity. 4 to the 1 over 2 over x minus 1. Being equal to. Now when we evaluate our limit, we can let x go to infinity. And this becomes 4 to the 1 over 0 minus 1 equals 4 to the negative 1 equals 1/4. That's it for this section. If you enjoy working on this, this ends up being kind of certainly a different direction than our trig chapter was, and some of you are going to be thankful that we're done with trig and we're launching into this. Some of you liked exponents and logs when we saw this in 30-1. Again, it's going to be a lot of similar stuff with derivatives and curve sketching and whatnot, but it ends up being there's going to be some different stuff in here too. All right, good luck. If you have any questions, please let me know.